Hello there. Welcome back to the 5th video in our series of Laplace transform online lectures. We've discussed some of the properties of Laplace transforms and how they can be applied to process control problems. We also have done some examples. Today we're going to look at a couple more properties of the Laplace transform that will be important as we encounter process control problems, and also look at a couple of tools that will be really important. Two properties of the Laplace transform will be really helpful as we try to gain more information about the time domain from the frequency domain or vice versa. The first is the initial value theorem. This theorem is going to allow us to figure out the initial value of some function f of t if we know the transfer function already. So in this case, we could, for instance, determine that the function at time equals 0 is equal to the limit of that product of this Laplace variable s and our Laplace function y of s as s goes to infinity. So this could be very important. This is that initial value that we often need. The final value theorem follows along the same general idea that really as time goes to infinity, s goes to 0. This concept's quite important and we see it frequently. The final value theorem allows us to find out the final or steady state value of a function from its transform. So if we need to know the function at some large time when our process has approached steady state, so that could even be, approximated as 5 times the time constant. If you recall, that's 99% of the way to steady state. This value is equal to the limit of the product of our Laplace variable s and that Laplace function f of s. And this is as s goes to 0. So the big concept here is, remember that as time goes infinity, s goes to 0. As time goes to 0, s goes to infinity, and we can relate these two concepts. Okay, the next tool we'll need to have in our toolbox is linearization. So as we know, Laplace transforms can be applied to linear ODEs. Only to linear ODEs. This means that we'll have to conduct linearization when we encounter nonlinear ODEs. So this happens all the time, especially in dynamic process models. For example, if you're doing a reactant mass balance on almost any chemical reaction, you'll see nonlinear ODEs occurring. So this is pretty neat because we can actually linearize any function. So for example, if you have a function that has one variable, so you have a function f, and there's only one variable, but it's nonlinear. So for example, it's f to the 4th power, something like that. You can actually linearize, where this is a function of x, by the way, f of x. You can actually linearize this function by applying this formula. So we could say that for, in this case, f bar is a constant. Here, if we take the first derivative of that function f and evaluate it at the steady state condition, it turns into a constant, and then we can just multiply by the difference between the natural variable x and its steady state initial condition. Suddenly we have this linear approximation of this nonlinear function f. Additionally, we can carry out this operation in the case that we have a function of 2 or more variables. So in this case, we have 2 or more variables showing up in this function. It's nonlinear. we can actually just conduct the exact same process on each variable. So we'd have the initial steady state condition, just as we had in the one variable form. Then we'd have this same term where we take the derivative of that function with respect to the first independent variable x, evaluate it at the initial steady state conditions. That's going to be a constant after this operation, and multiply it by this difference between the natural variable x and its steady state condition. So this, if you recall, is the deviation variable x prime. Okay, so then we're going to sum that and repeat the exact same process with the next independent variable. So in this case, the next independent variable is y, and we multiply it by the deviation variable y prime. Okay, so as you can see, if there were more variables than that, you'd continue the same process and continue in this until you've linearized the whole equation. All right, so we see how we could do this for functions. We can also do this for ODEs. That's really important because that's kind of our goal, solving nonlinear ODEs by linearization before we can use the Laplace transform. So in this case, we have some ODE, and it contains nonlinear terms. So it has some function g, in this case, that is nonlinear. We need to linearize this function in order to solve it. So very similarly, we can linearize this by using the same approach. So we take the derivative of the function g with respect to the first variable and evaluate that at the initial steady state conditions. This becomes a constant. Okay, then multiply it by the deviation variable x prime, which is the first independent variable. Then we continue this process with respect to the next independent variable. So the derivative of that function g with respect to y, the second independent variable, evaluated at the initial steady state conditions, it also becomes a constant, and multiply by that deviation variable. Okay, you'd continue this on until you've addressed all the independent variables that were showing up within that nonlinear term. Okay, it's pretty useful. You'll have a chance to practice it on the homework. Okay, the next tool I'd like to talk about is partial fraction decomposition or expansion. These terms are used interchangeably depending on the source. Okay, so often we'll encounter some sort of function in the Laplace domain, so some sort of Laplace transform solution y of s. And we'll probably be interested in inverse transforming this function to take it back to a dynamic model. However, that denominator of most real solutions to dynamic functions are often a high-order polynomial. That can be a real problem because it's hard to find these high-order polynomials in any sort of Laplace transform table. So by using partial fraction expansion, we're able to manipulate this function so it actually is the sum of lower order denominator fractions. So doing this, we can really reformulate y of s into some terms, and based on the linearity principle of Laplace transform, we can handle each of these terms individually and find them in the Laplace transform table to inverse transform. So as a very general example, we can see that we may have some function y of s that looks something like this. Okay, we have some stuff in the numerator, some sort of function of s, and in the denominator we have this third order polynomial. So you can be clever. There's multiple ways to do this, but especially if you were doing this without the table, you may want to have some reduction to a form you easily recognize. For instance, I realized that this first term will likely be a constant, and the subsequent terms would be exponentials, and I know those by heart. So in order to do this, we realize that if we can break the denominator up into different sums whose products, the individual terms in the product, would be a good denominator in order to find the inverse transform, we can then conduct a little algebra to figure out what the numerator of that fraction should be. Also, it's really useful to memorize, and I encourage you to do so, the quadratic equation. Remember, when you have a second order polynomial, you can apply the quadratic equation to determine the roots of that polynomial. So here you could see in this most general form, the roots of this polynomial are showing up here as R1 and R2. Okay, so let's look at an example with some specific numbers. So in this case, we see a similar form, except now we actually have some numbers to figure out. And we're going to be able to determine this simplified sum of fractions where we're able to easily find the inverse transforms in the Laplace transform table. So let's see if we can accomplish that. The first thing we need to do is determine, first of all, we have this s, so we can obviously factor out s. And then we have a second order polynomial. We need to find the roots of that polynomial. Okay, so when we expand this, we can calculate that. You could plug it into your calculator. And I actually found, let's see. Okay, so, oops, sorry about that. By this method, I determine that R1 is equal to negative 46/3, and R2 is equal to 32/3. Or alternatively, you're able to factor this if you could figure out a way to factor it. So these are the roots. Obviously, this is what we'll do. So now when we plug this in, we can actually see that we get 2 plus s over s times 6 s squared plus 16s plus 8, okay, is equal to alpha over s plus beta over s minus r1 plus gamma over s minus r2. All right, so the next thing we'll do is actually multiply the right side by the denominator from the left side. So by doing this, I actually get 2 plus s is equal to, in the first term, the s is going to cancel out on the bottom, so it's actually alpha times 6s squared plus 16s plus 8. Okay, when we do it with the next term, we see that s minus r1 is going to cancel out, and we'll end up with beta times s minus r2. See, r1 and r2 aren't round numbers, so I'm not going to write those out over and over again. Just leave it r2, it's defined above. And now the gamma term will be gamma times s minus r1. That s minus r2 cancels out. All right, so now we can kind of distribute this and put it together as groups. Okay, so here, let's see. Pause it. Okay, so when I am breaking down these polynomials, I like to write out the different powers of s. So we'll have s to the 0, which obviously is no s, like this term 2 in the left-hand side, s to the first power, so that's just s, and then s squared. And then I'm going to write an expression representing each one. So here for s to the 0, on the left-hand side I have 2, and on the right-hand side I have alpha 8 in that first term. In the second term, there's no term, but this first term is s squared, and then the next one, the s will be distributed. So, and then the third term, there's no s to the 0 term. So here directly I can solve for alpha, that unknown constant, and I get alpha is equal to 2 over 8, or 1/4. All right, so in the next terms, I'm going to look for powers of s to the first. So just s. On the left-hand side, the coefficient of s to the first is 1. Okay, in the first term on the right-hand side, we have alpha times 16. Okay, notice I'm not writing the s's here. It's just a function to find those alpha, beta, gammas. In the second term, I have negative beta times R2. Okay, and in the third term, I have negative gamma times R1. Okay, also remember that I know that what alpha is already, so that's actually not an unknown. Okay, so now for power of s squared. There's no powers of s squared on the left-hand side. I'll write a 0. Okay, here we'll have alpha times 6 from the first term. Beta, just beta, there's no times 1, and then plus gamma. Okay, so now we have two equations with two unknowns. We need to solve that system of equations. So we can do a few things. So usually I'll use back substitution, or you could use a little matrix, that would work too. So let's just solve for these unknowns. So here in the first one, I see that I can solve one for the other. Let me solve this for... Okay, so I solved this system of equations, and I've determined that beta is equal to negative 19/26, and gamma, hold on, this one was gamma, this one's gamma, I apologize, and beta is equal to negative 10/13. All right, so I can go back in and rewrite this equation so that I can easily transform it. Remember that y of s now can be defined as alpha, so I could pull it out 1/4 times 1 over s, which it's very easy to find the inverse transform of that term. It's 1/4 times 1, plus beta, so this is negative 10/13. I'm also going to pull out that R1. So 10 over 13 R1, it's up there at the top, multiplied by this quantity 1 over negative 1 over R1 S plus 1. Okay, so here that's just an exponential term with tau equal to negative 1 over R1 plus our last term, negative 19 over 26 R2 times 1 over negative 1 over R2 S plus 1. Okay, also when we take the inverse of that term, it'll be a constant times that inverse. Okay, so that problem was a little messy, but as we see, partial fraction decomposition will allow us to find those identities on the Laplace transform table and really use them.